Okay, so Chapter 6 of OpenStax Volume 2 deals with electric flux and Gauss's law. So, the first thing we want to do is define the quantity of electric flux, because this is going to be a key quantity that we're going to be able to use, something that Gauss first noted, to be able to actually calculate some particular electric fields. So what do we mean by electric flux? Electric flux, sometimes called phi sub E, is sort of defined as the number of field lines, electric field lines, through a surface. This is the way to think about it. Electric field lines through a surface. So what do I mean by that? Let's take a simple example. Let's have, in fact, I'm going to do electric fields in red. So I have an electric field here in the plus x direction, okay? And I'm going to send it through a surface. So the surface, trying to do this kind of in 3D, the surface is in the YZ plane. I've got X, Z, let's see, and then Y would be back out that way. So yeah, this surface is in the YZ plane. Let me see if I can kind of illustrate this. So if it goes in like that, you see what I'm saying? Yeah, it's going to thread through there. So something like that. Now, the way that we define electric field is as the electric field dotted into the surface area. So basically, it's E dot A, or it's the electric field times the area of the surface that the electric field lines go through. So the trick here is that I want to be able to, I'm going to take the same set of electric field lines, but now I'm going to rotate my surface so that, let's say that it's now in the XY plane. Okay? And so if I try to send an electric field through there, well, it doesn't thread through there because it's in the same plane as the electric field line. So the flux here, which would be E dot N times A, okay? In this case, up here, it's just going to be E times A, because all of the electric field is perpendicular to the surface normal, and therefore E dot N hat would just be E. I mean, think about it like this. This electric field is equal to some, let's call it E0 in the x hat direction, okay? Same thing here. The electric field is E0, that's the magnitude of it, and it's in the x hat direction. So if I put that here, I'd get E x hat, and the N vector is also x hat. N hat is x hat, it's in the same direction. Well, x hat dot x hat is just 1, x hat dot x hat. And so E dot N hat here is just E0 times A. Okay? Well, the same thing's true here, except I get E0. Now E dot N hat. Now here the N hat is in the Z direction. N hat equals Z hat. And so if I do E dot N hat, I'm doing E0 x hat, that's E, dot Z hat. But x hat dot Z hat is 0. And so this would be 0. Which makes sense. That's what I'm saying. The flux quantifies how much of the electric field gets through a surface. So if all the electric field gets through the surface, it It's the magnitude of the electric field times the area of the surface. If none of the electric field gets through the surface, it's 0 because there's no electric field actually threading through the surface. Okay? So the key thing here is the area vector, the way that the area vector is defined. And so what would happen if I had, let's say, a partial electric field? Let's do this case here, where I might have this E field, same as before. E is equal to E0 x hat. Okay, that's great. But now I'm going to place the surface so that this is going to be kind of hard to draw. Let me see if I can do that. Okay, not exactly sure how to do that. So that n hat, okay, is out this way at an angle theta with respect to the x direction, right? And what I would say here is that n hat is equal to, as we're looking at it, if I've got this rotated right, I'm just rotating it up into the z direction, right? So it's going to be cosine theta, cosine theta x hat plus sine theta z hat, right? I've just rotated it slightly up into the z direction. Again, remember x, z, and then y is out that way. So that means that E dot n hat would be E0 x hat dotted into cosine theta x hat plus sine theta z hat. And that would be E0 cosine theta x hat dot x hat plus E0 sine theta x hat dot z hat. And of course that is 0 and x hat is 1, so that's just going to be E0 cosine theta. So E dot n in this case is E0 cosine theta. Then the flux would be equal to E0 a cosine theta. E dot n hat a. Okay? Now occasionally you might have surfaces where they vary. It's not well defined like this, and maybe you need to integrate over a surface, in which case you can talk about a differential element of the flux, but you can define it in the same way. It's just going to be equal to E, because the electric field should be about the same, dot n dA, and that's the way that we sometimes see it. In fact, some books will call dA a vector in and of itself, but dA is understood to be the magnitude of dA in the n hat direction. Okay, so if I have an arbitrary surface, then I can say this: the electric flux is equal to the integral over the surface of E dot n hat dA. Okay, we'll see that. We'll do several examples like this when we do examples for the homework. Okay. So that would be the flux through an arbitrary surface. If the surface is a closed surface, we can indicate that just by integrating over the entire closed surface. And this is going to be important in our understanding of Gauss's law. So we want to make sure we understand what electric flux is and how to calculate it. So there are some examples that they give in section 6.1 where you can look at electric flux. They give you an inhomogeneous electric field in example 6.4 where you have to integrate because the electric field is dependent on the y component of the surface. So so that's basically the introduction to electric flux that allows us to then define what Gauss's law is, which is the next video.